So I think we can get started. And last time we looked at, within the context of special relativity, at tensors and vectors. So the first object, of course, we became familiar with was just ordinary vectors, right? And so here is an example of what I wrote already on the blackboard last time, where you have a vector which has an index up, and it transforms on the Lorentz transformation in this way. So of course the classical example for that is x alpha, right? So x alpha is x and t, so that's a naturally contravariant tensor, right? Now you will and want to introduce an entity which has an index downstairs, right? An index downstairs, and so it transforms in a slightly different way with a matrix that is defined as the inverse of the matrix that we have here. Right, the inverse of the matrix. So that means that this new matrix, where you see the indices are arranged slightly differently, is such that the product of the old one, which is this one, times the new one gives the identity. Right. So the correspondence is that now you have x alpha, and that would be x and minus t, because when you do this inversion in special relativity, you don't do a whole lot, you just reverse the sign of the time component, right? That's no longer true in general relativity later on, but here it's just the difference between a covariant and a contravariant is not a whole lot, right? It's just basically the sign of the time. But it is necessary in this formalism, and certainly in the case of general relativity, to make a distinction between the two, because the dot product between four vectors does not involve this dotted into itself or this dotted into itself, but involves the product of this into that, so that the sign of the time comes in the correct way, right? So that means that if you take, so therefore, if you take u prime alpha and v prime beta alpha with index up, now like this, right? So this one is covariant, and this is contravariant, right? Then the transformation law is what we have over on that side. So this is equal to lambda alpha gamma for the first one, right? And lambda alpha beta for the second one. Lambda alpha beta for the second one, and then times u gamma v beta, right? And because of this relationship that you have here, this is just a Kronecker delta, right? So this is the same as u alpha v alpha, and so that means that this alpha. So that means that this is an invariant. An invariant dot product between four vectors. So it is essential that you have an index up and an index down, right? And so that is the reason why you have to distinguish between covariant and contravariant vectors. And the other thing is that you can always make a covariant vector into a contravariant one, and vice versa, by using the eta symbol, right? So that means that v alpha can be written as eta alpha beta times v beta. So you can go from an index up to an index down just by multiplying by this eta matrix. Now remember that eta alpha beta is just equal to -1 and then +1, +1, and +1 along the diagonal, and 0 everywhere else, right? So so-called flat metric, right? And similarly, you can make a vector that has an index upstairs, right, u alpha. You can make that eta alpha beta u beta. You can make the index that is up to become a downstairs index by again using the delta, the eta symbol, right? So this is called, I don't have much space here, maybe I can write it down here. It's called raising and lowering indices. Raising and lowering indices. So in other words, if you have a vector, right, like this, you can put the index upstairs or you can put the index downstairs, right? So not both at the same time, so maybe I should have this square as a dotted square like this, right? So they are essentially the same thing, whether the index is upstairs or downstairs, because the only difference is the multiplication by this matrix. Nevertheless, there is a slight change in the sign of some of the components because of the appearance of this Lorentz signature, right? The -1 that always comes with the time, right? So doing a dot product with a vector that has an index upstairs and an index downstairs ensures that you get the right sign, so that when you calculate x squared, you have actually x squared plus y squared plus z squared minus c squared t squared as the dot product of the x vector with itself, right? So you get this correct sign, right? So this is what is achieved here, is by having a dot product of a contravariant object with the plus here with a covariant object with a minus, that you have the right product. Of course, if you were in Euclidean space, right, if you didn't have this strange sign for the time, then in Euclidean space there would be no need for this distinction between covariant and contravariant, because the dot product will always have the plus sign, right? So now one object that we often have to refer to and use is the gradient, right? So here we also have, of course, a gradient with 4 indices, a single index that takes on 4 values. So we have gradient, and the gradient is naturally covariant. Covariant because if we take d by dx alpha, right? Now remember, when you have the index up, this is x and t, right? So it's a natural object. So when you do a Lorentz transformation, right, then this goes into a dx prime alpha like this, right? And now we can just use the rule that this is equal to dx beta by dx prime alpha times d by dx beta. Right? You can write it in this way by just multiplying and dividing by differentials. And now remember that x gamma is equal to lambda gamma delta times x delta prime. Right? The transformation law for the coordinate is equal to this. So you can solve for x delta in terms of a lambda to the -1. And so dx beta dx prime alpha, which is what we have up there, is equal to lambda alpha beta. Lambda alpha beta, like this. And so that is, I think I already erased it from the blackboard, that this was precisely the object that was relevant for the transformation law of covariant vectors, right? So d by dx alpha is a covariant vector. Right? So that means that if you want to construct an invariant, then you have to multiply it by something that is contravariant. Contravariant meaning that the index is upstairs. Right, so that means that d by dx alpha times v alpha, or actually also v beta, but dx alpha, this is invariant. This is invariant. So this would be like a 4 divergence. Right? So this object, even though the index here is upstairs, acts like an object where the index alpha is in fact downstairs. Right? So as a consequence, another object which is invariant is if you take d by dx alpha and d by dx beta, if you take this combination, which acts like it has both indices downstairs, and then you multiply this by eta alpha beta, which has both indices upstairs, then this is an invariant as well. and it is equal to the gradient squared minus d by dt squared. So this is equal to the D'Alembert. Equal to the D'Alembert, right? So the equation that the operator that appears in the wave equation is in fact invariant because of this property of the gradient. So now we have more general tensors. So far we had we had scalars which have no indices, right? Objects that have no indices. We have 4 vectors, right? Of which we have both the u alpha and the v beta, right? Depending on whether the index is upstairs or downstairs. But we can have more general entities such as more general, something that is T alpha beta gamma, for example, right? And this is equal this will transform, and let me put the index for clarity. Let me put this index upstairs here as a gamma and this as an alpha and beta. So let me write it as gamma alpha beta with the prime. This object, which has in the first position, by the way, the position is important. So in the first slot, it has an index which is upstairs. In the second and third slot, it has an index which is downstairs. This vector will transform in a way such that it is covariant in the indices alpha and beta and contravariant in the index gamma, right? So it means that it transforms according to lambda gamma delta. For the first index, right? And then lambda alpha and lambda beta for the second 2 indices with some other dummy index which we're going to call epsilon and psi here, right? And times the original tensor which has an epsilon and xi here, and it has a delta up there, right? So that means that this particular tensor is contravariant in the gamma index, in the index upstairs, and it is covariant in the 2 lower indices, right? So this in particular is a case of a mixed tensor that has some indices which behave in one way and some other indices which behave the other way, right? And so in general, we have a tensor which has an index up here and then has 2 indices down there. And these indices can be raised or lowered using the eta symbol. So you can bring this index from up to down, bring it down here into this slot, and it will be the same tensor, but the index will be in a different location, so it will be the covariant version in the first index as opposed to the contravariant one. So anyhow, this is some of the tensor manipulations that you can already do in the context of special relativity, even though, as I said, it is somewhat trivial in this case, because in many cases all you're doing is just switching the sign of the time component. Nevertheless, it is non-trivial in general relativity, and so that is one of the reasons why we already get started early in doing this exercise of raising and lowering indices, right? So the next question is how to make a tensor. How to make a tensor? Well, of course, one possibility is somebody gives you an object which is already a tensor, and then you manipulate that. But you can also construct a tensor by having some elementary components to it. And the first possibility is linear combination. So you can take a linear combination of 2 tensors, and that will still be a tensor. So for example, you can take T alpha beta, right, which is alpha times R alpha beta plus let's call it C1 so we don't confuse it with the indices. C1 R alpha beta plus B, or C2, times S alpha beta. So if you have two tensors and you take a linear combination, that will still be a tensor, right? For the simple reason that you determine whether it is a tensor or not by acting on it with the Lorentz transformation, which is the matrix, right? So a linear combination of two vectors is still a vector in three-dimensional space, and here we're in four dimension, it's the same story, right? So a linear combination is useful, yes?
So then that's the definition of a tensor, something that transforms like?
The definition of a tensor is something that will transform in the appropriate way. So it will if it has three indices, it will transform with three lambdas, and the lambdas will be one type of lambda or the other type of lambda, depending on whether the index is upstairs or downstairs, right? If it has four indices, then there's four lambdas, right? So. And so that is one possibility, is to take a linear combination, and the other possibility is to do a direct product. In other words, if you take A alpha and beta and B gamma, then this is also a tensor, and it is a tensor that inherits the correct tensor properties from the original tensors, right? So this one is a purely contravariant one. This is one that is contravariant in the first index and covariant in the second index. And so this tensor has to maintain that structure. So it will have one index up here, a second index down here, and then the third index down there, and this slot here is going to be empty, and that slot is going to be empty, right? It's very important to maintain the correct position, right? And so this is a tensor that is neither covariant nor contravariant. It is mixed, right? It's got some indices that are upstairs and some indices that are downstairs. And, you can always bring them up or down using the eta symbol, right? So if A and B are tensors, then T is still a tensor because the transformation properties are determined by a product of lambdas, and there are going to be some lambdas acting on this and one lambda acting on that, and so everything goes through cleanly, and that is a tensor. Right, so another thing that we can do is a contraction. This, by the way, is a direct product. Right, so this direct product, right, where you don't sum any indices over, you just take the product. So a contraction is one where you take an object, right? Again, let's call it T, and let's take T alpha beta, and you take T again, and you have T beta and delta or gamma, right? Like this. So that means you take a product of the tensor with itself, or maybe with some other one, it really doesn't matter. And you contract the two together, or you can even take the same tensor, T alpha beta, beta gamma, and do something like this. And again, you sum over two indices, and those indices then disappear. Right? When you sum them over, they're gone, and so this behaves like a new entity, which we're going to call by a different name, for example, S. And it will be a tensor that has an index upstairs and an index downstairs. So this is called contraction. Contraction means you take two indices, you make them equal, and you sum them over. And those indices then are kind of gone. I mean, they're no longer free indices, right? And so the fourth thing we can do is differentiation. Right, differentiation, this is an important aspect of this, and that is that we can take T beta gamma, and we can take the derivative with respect to x alpha, right? And this will give us a new object, which we can either call by the same name, or it would be perhaps better to use a different name for it, which we call S, which has an index beta and an index gamma, which is upstairs, and an index alpha, which is downstairs, right? And so this will be also a tensor. It will be a tensor because we're assuming that this T is a tensor, and we know that the derivative is also a tensor, right? And so it would allow us to construct allow us to construct a genuine tensor out of that procedure. So as you can see, if you're given a tensor, there's lots of ways to construct more tensors out of them, right? So there's all sorts of operations which maintain that tensor character. So now there is a number of special tensors which are useful, right? And one is the eta symbol, right? So eta, alpha, beta, the so-called flat metric, right? Now you remember that this has the property that lambda, gamma, alpha, lambda, delta, beta times eta, gamma, delta, that this relationship is true. We saw that in the second lecture, right? This was kind of the statement that the lambdas are orthogonal transformations if we were in Euclidean space, right? That lambda times lambda transpose is equal to 1. So this is the corresponding statement for a Lorentz transformation. And it is true. And as a result, though, by staring at this relationship, we can see that when eta is transformed by a Lorentz transformation, is first of all, it still gives a tensor, right? Because it still gives eta alpha beta, which is a two-index object with indices downstairs, which is a tensor. But it happens to be exactly the same tensor. So this is transformed, but it's transformed into itself, which is kind of nice, right? And so that can happen too, right? So this is form invariant. It is form invariant, so it is a tensor. It is, in fact, a covariant tensor because the indices are downstairs, but it maintains the same form, right? Another one which does the same, so that's example number 1. Another one is the one which we obtain when we do eta alpha beta, eta beta gamma. This is a tensor. That is a tensor because we just shown that that is the case. And we do, in this case, one of the things that appears on that blackboard, which is item number, so-called. We take two indices between the two and sum them over, right? In this case, we contract over the index beta, right? And as a result, we end up with an object that has an index upstairs and an index downstairs, which is also going to be a tensor. But in this case, we know, if you look back, or if you remember the explicit form of eta, we know that this is simply delta beta gamma, the Kronecker symbol. Right, is the Kronecker symbol. So the Kronecker symbol is another example of a tensor that, first of all, is a genuine tensor. Secondly, it is a mixed tensor because it has one index upstairs and one index downstairs. And thirdly, it is form invariant. Right? And so alpha gamma. So the third case is the epsilon symbol. Right? So if you take epsilon, alpha, beta, gamma, delta, right? And so this epsilon or Levi-Civita symbol is equal to +1 for epsilon, for alpha, beta, gamma, delta equals 0, 1, 2, and 3. Right? So it's the standard definition of the epsilon symbol generalized to 4 dimensions. Right? Normally, what you're familiar with is epsilon ijk. Right? Epsilon ijk. And so it is +1 if the indices are in the canonical order. It is -1 for any odd permutation. So alpha, beta 1, or even permutation of indices. It is -1 for an odd permutation of indices. And it is 0 otherwise. Right? And so that is a tensor as well. It is a tensor as well, even though we'll not prove it here. And and that is also form invariant. So theorem, last theorem is, and all these things survive in general relativity. All these things survive in general relativity, which means that it's still going to be true even when we deal with more general coordinate transformations, that we can do things like tensor addition, tensor direct product, tensor contraction, and so forth, and we still get tensors, right? So this all carries over, and as a result of that, it's quite useful. And now we have a theorem. And, well, let me say that in words. The theorem is that if two tensors, right, if two tensors, which have the same number of indices upstairs and downstairs, so I have these two tensors, and this one has one index upstairs and two indices downstairs, and I have a second tensor here, which is, again, with the same number of indices upstairs and downstairs. If these two tensors are, well, first of all, clearly tensors, right? And secondly, if they are equal, right, in one coordinate frame, then they will be equal in any coordinate frame, because the difference between the two, T alpha beta gamma minus S alpha beta gamma, if that is 0 in one frame, then when you do the Lorentz transformation, it will still be 0 in any other frame, which means the two tensors will be identical, right? So if they have the same number of indices, then the equality of these two tensors is a Lorentz invariant statement. So if they're equal in one frame, they'll always be equal. And that's the importance of being a tensor, right? If you're not a tensor, then that's not going to happen, right? So the central meaning of a 4-vector, 4-tensor, and so forth is that out of those objects, you can construct things which are invariant. You can construct equations that will be valid in any reference frame, right? Because of the transformation properties of tensors. Remember, the transformations law are linear for both of these. So if the difference vanished then in one frame, then it will always be 0. Okay, so this is the short introduction of tensors and the generalization and manipulations that we have in special relativity. So now we need to talk about a few other things, which is conservation laws, and in particular a little bit of current densities and topics related to electromagnetism, right? And then something that is closely related to it, at least at a formal level, which is the energy momentum tensor. Then angular momentum, which comes out of this, right? And then the last topic we're going to talk about in special relativity is the perfect fluid, which is kind of unrelated to the first three things, but the perfect fluid is important if you want to do any sort of simple cosmology. It's usually the type of matter that is brought into. So let's get started first on the current density and electromagnetism part. And what I want to show you is that the current density in electromagnetism can be written as a 4-vector. So what we first do is we write down the current, right, for a single particle, or maybe a combination of particles, but it will be simplest to just deal with a single particle, right? So we have a single particle that follows some trajectory, which depends on the time. And the current density, J of xt, well, it's the charge times velocity, except here we're talking about the density, so there has to be a delta function somewhere. So it is E times delta 3 of x minus x of t, right? And so that this current density is non-zero only along the path followed by the particle, right? And then times, of course, the velocity, right? So times dx of t along this trajectory times dt. All right, so that's our current density. And then we have the charge density, rho of x and t, and that has a similar form, right? It will be E times delta 3 of x minus x of t, right? And then there is, of course, no velocity term, right? So these are the four entities that describe an electromagnetic current, which suggests that we group them together into a J alpha, right? A J alpha, which depends on x, whose components are the J and the rho, right? And so this is a 4-vector, possibly, right? And so if we group them together, then we have that J alpha of x, right, is equal to E times delta 3 of x minus x of t, right? And then times, well, we have dxi by dt, and for the fourth one, we have, of course, we can write this as dt by dt, right, obviously. And so it looks like we have dx alpha by dt. Right? And so we can actually manage pretty quickly to group together these 3 plus 1 components into a single 4-vector, which in this case is contravariant because it has the index upstairs, which follows on the fact the coordinate has the index upstairs. And now this is obviously a 4-vector. Well, I don't know. I mean, it doesn't look like a 4-vector to me. Why is it that it doesn't look like a 4-vector, manifest 4-vector? Well, it does have some of the ingredients because it contains the coordinate x alpha, which we know is a 4-vector. But what seems to spoil the fact that it is a 4-vector, at least manifestly, is the presence of the d by dt, right? So if it had the d by d tau, which was the proper time, which is an invariant, then it would have been okay. But it contains the d by dt, and of course the t for one observer becomes a t prime for another observer, which is related to the first one by the length transformation. So this is clearly not invariant. So there's a first problem with this thing here, right? And there is a second problem with the factor in front of it, right? It contains a delta function only over x, y, and z, right? It's a delta 3, okay? So it doesn't look like it has the right properties to be a 4-vector. So we can certainly make this attempt at writing it this way, but it is not manifestly in this form a 4-vector, right? Well, it is, because I can rewrite it in the following form. I can rewrite it as an integral over proper time, d tau, right? And then I can write it this as E times delta 4 of x minus x of tau, right? So I can replace the delta 3 by a delta 4, which means I get an extra delta function in the tau variable, and then rewrite this as dx alpha by d tau. Now, if indeed this was true, if this rewriting was true, then do you think this is a good 4-vector? I would say the answer is probably yes, because it contains a 4-vector now, because dx alpha by d tau, where tau is the proper time, is a genuine 4-vector, right? And this delta function is now a delta function over 4 components as opposed to 3, which is good. And the final integration is over an invariant, which is this proper time. So this is manifestly invariant. This is manifestly invariant. The question is whether it's equivalent to the first one. And it looks like it's very close, but maybe not quite. But the reason that it is in fact correct is that, remember that delta x naught minus x naught of tau, right? So if we look at the fourth component here, right, there's a delta 3, and then there is a delta over the naught component, which is x naught minus x naught of tau, which is what I'm writing here, right? So that's one piece of it. A 4-dimensional delta function is a product of 4 deltas, just like a 3-dimensional delta function is a product of 3. Okay? So this one can be written as delta of tau minus tau naught, right? But we change the variable, therefore, to the x naught, which is the time, if you wish, to the proper time. But we know that when you do a change of variable in the delta function, you pick up a factor of, remember this, dt by d tau, right? It's this Jacobian, right? Remember the derivative of the argument of the delta function with respect to the variable, right? dt by d tau. And so now we can do the delta function integral because we have an integral in d tau, and the integral of delta function is 1, so that goes away. And what about the d tau by dt? I think it's better to be in this way. The d tau by dt that cancels out this d tau here and gives us the d by dt, and it gives us that original thing, right? So everything is okay. Right, so this thing is indeed a 4-vector. Right, it is a 4-vector, and the other thing that we might want to show, right, the other thing which we might want to show is that it is conserved. Right, so J alpha of x is conserved. Right? The reason why we do these things in a little bit of detail is because the same procedure is going to be followed in just a little bit when we do the energy momentum tensor. We're going to do exactly the same kind of steps. And at that point, I will just say you proceed in the same way as you did for the charge and current density by doing this kind of manipulation. So it is also conserved because what we can do is we take the divergence of J. Right? So remember, J has these components, right? So this is a spatial part. So this is nothing but the derivative with respect to the ith coordinate of the Ji. Right? So we just write in what the Ji is, because I have it right here on top. Right? So this is equal to E times delta 3 of x minus x of t times dxi by dt. This derivative. Okay. Now the d by dxi acts on this x here. Right? And now what we're going to do is we're going to make it act on this one instead. So we use the fact that d by dx of delta of x minus x naught is equal to minus d by dx naught of, with the index, let's leave the upstairs, minus d by dx of delta of x minus x naught, where this derivative is with respect to the argument here, whereas in this first case it's with respect to the other argument. Right? So you can transfer the derivative on one or the other thing. So we can rewrite this as minus the derivative with respect to x of t. So this is equal to minus d by dxi of t, right? So we make that explicit by writing an xi of t, so we know what the derivative is with respect to, and of e times delta 3 of x minus x of t, as before. This part is unchanged, right? And then times still this derivative which we have up here, which is dxi by dt. Dxi by dt. And now you recognize that dxi by dt times d by dxi is nothing but the derivative with respect to time. In other words, this one and that one combine together to give just d by dt. Right? Let me write it as a partial d by dt. Right? So this is equal to minus d by dt of what's left over is, of course, this piece here, and that piece is the rho, right? Because the rho is just an odd component. And so we have the continuity equation that divergence of J plus d rho by dt is equal to 0. Through these manipulations that, well, of course, you might not be particularly happy of taking derivatives of a delta function in this way, but nevertheless, you can always make this delta function a little bit smoother, and then these manipulations will be correct. So here, in any case, we only use the fact that you can transfer the derivative from one argument to another, and you get that this is conserved. So everything seems to work out nicely for this current density, right? So that means that we have that d by dx alpha of j alpha is equal to 0. So this is a continuity equation, right? So we've been able to prove, right? We've been able to prove that for a single particle that is described by a current density and a charge density, the way we just did it here, that that current and charge density can be grouped together in a 4-vector, and it is a genuine 4-vector. It is manifestly invariant because it can be written in terms of 4 vectors and scalars, and also that it is conserved, right? So it has all the right properties, and so that's for a single particle, right? Now, if we're dealing with electromagnetism or electromagnetic interactions, then there is a second component that we want to bring up, which is the electromagnetic field itself. Right? So we have dealt with this J alpha, right, which is the J and the rho, right, and which is conserved. Conserved 4-vector. And now we have to deal with the other half of the problem, which is electromagnetism or Maxwell's equation, right? Because we want to couple this particle to the electromagnetic field. So we have, for the electromagnetic field, we have the divergence of E is equal to rho, right? And that the curl of B is equal to J plus dE by dt, right? And so these are the two source equations, if you want. Right, so we're going to call this 1 and 2. And then we have the other two equations, 3 and 4, which do not involve sources. And so that is the fact that the divergence of B is equal to 0, the absence of magnetic monopoles, and that the curl of E is equal to minus dB by dt, which is Faraday's law. So we want to now rewrite this as in terms of 4 vectors and possibly tensors. Right? So it would be nice if we can do that, and that is fairly easy to do because the first thing is we introduce a tensor that has indices, right, 2 of them, in this way, and whose entries are as follows. So with, first of all, Fij, so the spatial part of this tensor, Fij, is equal to epsilon ijk bk. Right? By the way, when you have spatial indices, doesn't matter whether you put them upstairs or downstairs because there is no distinction. It's the time that always causes these issues, right? So when you have indices ij and k, you can put them anywhere you want. The result is the same, right? So we define the spatial components of this f mu nu to be equal to that, and that leaves the f naught j, which we define to be the B field. Right, so this is equal to Ej. And so those are the entries, right? And so now we want to write, right, so the x and y components of this are equal to Bz and cyclic permutation. So now we want to rewrite the first two equations in terms of this f. And the first two equations are that d by dx alpha, f alpha beta is equal to minus j beta. So that's equation 1 and 2. And I'll leave that as an exercise for you to convince that this is actually the case. So in other words, you take for this f, these various components, And you can see that you can either reproduce this equation when you have the I and j components, or you reproduce this one when we have the naught and j components. So that equation, of course, looks rather nice because it involves on this side a 4-vector, and it involves the d by dx alpha, which we know is also a naturally covariant 4-vector as well. Right? So these are the source equations. And what about these other equations here? So let me write it out over on this side. So 1 and 2 give d by d x alpha, f alpha beta is equal to minus j beta. And 3 and 4 should give something that is equally simple. And in fact it is, because they give epsilon alpha beta gamma delta d by dx beta f gamma delta is equal to 0. Right? Again, I'll leave that as an exercise for you to be convinced that this is indeed the case. Right? The second one can be written in a slightly equivalent form, which is that d by dx alpha f beta gamma plus d by dx beta f gamma alpha plus d by dx gamma f alpha beta is equal to 0. And that's the same form. The two are the same. And if any of the indices are the same, then this vanishes, because if you take two indices that are the same, then this thing is antisymmetric, so you get 0. So the only case in which this expression is useful is when all the indices are different, alpha, beta, gamma, beta, beta, gamma, alpha, beta. So when all the three indices are different, then you get something useful. It's exactly the same as that, and it is the same as the source-free equation. Source-free equations. So that's kind of neat that you can rewrite Maxwell's equations in a form that involves this 4 vectors. And this J is a 4 vector. This is a 4 vector. And so we expect this object to be a 4 vector too. And it is, indeed it is, because f prime alpha beta is equal to lambda alpha, lambda beta, and then gamma delta, f gamma delta. And so that is a Lorentz tensor. So the electromagnetic field is in fact a Lorentz tensor. It behaves in the way that we described before for something that is a well-behaved and genuine tensor. Now, one last thing that you might be curious about, what is the last thing that you might be curious about, is that when you have a particle that follows a certain trajectory and you have an electromagnetic field that is described by this f mu nu, then you should be able to solve what? You should be able to solve for the equations of motion, right? Right? And the equations of motion are F equal ma. Right? They are F equal ma, which we want to now write in a form that is consistent with everything that we discussed so far. So it should be something that is manifestly invariant. So it will involve the mass and the second derivative of the coordinate with respect to the proper time. Right? So this is what we wrote, I think, in the previous lecture as the analog F equal ma, where what appears on the other side is this 4 force. Right? And so we want now to be able to write down what this 4 force is, right, in electromagnetism. For electromagnetism. Well, we do know that the force that is acting on a particle when it is of electromagnetic origin will contain the charge, right? So that part is obvious, right? What else should it contain? Well, it should contain the electromagnetic field, right? Because the force on a particle, if it is electromagnetic, then it will involve the E and B fields, right? Now, we know that the E and B fields are described by an F alpha beta, right, in our case. Okay. So we're going to put that F in here, right? The other thing that we do remember is that in electromagnetism, well, in electromagnetism, of course, the relevant force is the Lorentz force, which describes the interaction of a particle with electric and magnetic fields. And we know that that involves the velocity, right? So the velocity has to appear somewhere on the right-hand side. The other thing that we do notice is that there is a single index here, whereas this object has 2 indices, right? And so those 2 indices have to become 1 at some point. And so it has to involve the velocity, right? And so we're going to write the velocity as dx gamma by dt, right? No, because we cannot use the t because the t is coordinate dependent, right? So a better candidate would be d by d tau, and that should work, right? Because that turns a 4 vector into another 4 vector because the proper time is an invariant, okay? So now what we have to do is kind of reduce that index, the 3 indices that we have there, reduce it to a single index alpha over on that side. And so that could be done by doing this, right? This index here is upstairs, so what has to appear here is a downstairs index and then another index upstairs there, right? And so now again, I will leave as an exercise to show that if you write these equations out in components, if you write out in components, then you will get dp by dt is equal to E times the electric field, right, plus V cross B, which is the Lorentz equation. Right. Is the Lorentz equation approximate? No, it's not. The Lorentz equation is actually relativistic, right? So it has everything you need in it, right? And provided at least you write it in terms of the relativistic momentum, right? And so you can derive this from that, right? All you have to do is insert for F alpha beta its components in terms of the B and E fields. And for this, you just introduce the velocity, right? So dx by dt becomes just the velocity, etc. Well, maybe, but what could be a concern? It could be a concern is that in fact we do have, in this case, 4 equations, and this one is only 3. So somehow we seem to be losing 1 equation along the way, right? And so what is the 4th equation here? The 4th equation will tell us when alpha is equal to naught, right? The 4th equation will give us the second derivative of t with respect to tau squared, right? And so the 4th equation is the one that allows us to eliminate the tau and write the t as a function of the proper time, right? So there's always this 4th equation that establishes this relationship, the relationship between the time and the proper time. Well, the proper time is an invariant, whereas the other time is not, right? So this equation refers to a particular coordinate system. So anyhow, this is kind of neat that you can write down the Lorentz equation as a 4-vector equation, and it has all the right properties that you expect, right? So So now we leave electromagnetism, at least for a few seconds, because we're going to come back to the electromagnetic field itself in a little bit. But let's discuss now. We talked about the current and charge densities, right? And now we're going to talk about the energy momentum tensor. So that is going to be a tensor. Well, this energy momentum tensor is going to be denoted by two components, so it will look like T alpha beta of x, right? And so what we have to try to do is determine what its components look like and what kind of conservation law, if any, applies to it. And so the first thing is that T alpha naught. So let's first look at the naught component, T alpha naught of x and t. It's going to look a little bit similar like what we had for electromagnetism, right? Because it will first be a P alpha of t, right? And a delta 3 of x minus x of t. Right? And that is the naught component, and it will be, again, we're considering the trajectory of a particle, right? And so it will be described by some x of t. And so this is what the naught component will look like. And you wonder, well, why is it in the first place that energy and momentum of a particle is described by an object that has two indices instead of one? Well, the reason why it has more indices, right, because the current and charge density were described just by a J alpha, which you remember was just J and rho, right? Well, in this case, it was enough to have a 4-vector because you can, from the continuity equation, which is divergence of J, right, plus d rho by dt is equal to 0, you can, from this, what can you derive? And this is something we always do in electromagnetism. You can derive that there is a conserved quantity, right? You derive that there is a conserved quantity, which is Q, which is the integral in d3x of rho of x and t, right? This is a conserved quantity. It's a constant which does not vary in time, right? And that is proven by exactly using the continuity equation, because you act with the time derivative on this. You get d rho by dt, which you can rewrite as minus the divergence. And the divergence is then a boundary integral, right? It's an integral at infinity. And using the divergence theorem, that is a constant. Sorry, the time derivative is 0, so that the q is a constant. And well, in the case of energy and momentum, do we have a conserved charge? Something has to come out which is conserved as well. We'll see in a moment, right? So what is conserved when you talk about conservation laws for energy and momentum? Not one charge, not Q, but instead 4. And which are the 4? The energy and, of course, the momentum, which has 3 components, right? So we need 4 conserved quantities, right, which are the energy and the momentum, the total energy and the total momentum, right? We need to have 4 of those, and in this case, we have 1 conserved quantity, right? 1 conserved quantity. Here we need 4, right? So the very basic fact that in electromagnetism there is only 1 conserved quantity, whereas when you look at energy momentum there has to be 4, tells you that the analog of this J in electromagnetism has to have more indices. Has to have more indices, right? And so, in fact, the answer is that it has to be a tensor with 2 sets of indices, right? So, as a result, we have, at least that would be the first thing to try, is to have 2 indices. And so we're going to take the naught component of this thing to be the P alpha. Why does that make sense? Well, the naught component here is the analog of the naught component for the current. When you integrate that, that is constant. Well, here it should happen too. When you integrate this naught component, it should be a constant, and that makes perfect sense because we have, in fact, the momentum. We integrate over all space, and we get the total momentum and the total energy, which is the naught component of P alpha. That should also be conserved, right? So this makes sense. This makes sense, all right? And so that leads the issue of what about the other components, right? So we have now T alpha I of x and t, right? And so that should be like a flow of momentum. And so the first component, of course, has to be, again, the same P alpha we have here, because this index here is unchanged. And so we need to have, in order to have the flow of the momentum and the energy, we need to have velocity appearing in here. And so that's dxi by dt times delta 3 of x minus x of t. Right. Very good. All right, well, if this is true, then we can group these things together, right, and make one bold step and define T alpha beta of x to be, right? There is a single expression which combines all of those together. And so that would be, again, P alpha of t for the first term. And for the second one, it would be dx beta by dt times delta 3 of x minus x of t, right? That works because if you take, in fact, the naught component, you get dx naught by dt, which is dt by dt, which is 1, right? So this combines the previous ones, right, into one single expression. So, yes? Yeah, it has dt by dt, which is 1. Yeah, dt by dt. If you bring this back to the previous one, you get dx naught by dt, right? So dx naught by dt is equal to dt by dt, which is 1. Okay, so there's a 1 here. Okay, so it works well. And so there are basically two questions that we would like to ask at this point. So question number 1 is the object we just constructed here at the bottom. Is it a tensor, right? That might not be obvious, right, from what we have, because, well, the P alpha part is okay, right? But this one is not, because it contains the derivative with respect to time, and also it has a delta 3 function and not a delta 4. And so we have to answer that question. And the second question we want to ask, which is again analogous to what we did in the case of electromagnetism, is it conserved? Very good. Okay, so we're going to answer the first question by doing the following. dx by dt, right? So dx by dt is just the velocity, right? But we can use the relativistic relationship, which is that the momentum, we can trade the velocity, if you wish, for the momentum, because this is what follows out of Einstein's relation between the energy and the momentum and the velocity. So that means that we can write P beta as E times dx beta by dt, right? When beta is equal to naught, then we get P naught, which is the energy, dx naught, which is the time, with respect to time is 1, so E is equal to E, so that works, right? So we're going to take that and use it for here. Right. Use it for here. So that means that we have a slight rewriting of T alpha beta of x, which you can write as P alpha of T and P beta of T divided by the energy times delta 3 of x minus x of t. Okay? Well, it's a slight rewriting, and of course it's still obviously at this point not manifestly Lorentz invariant. Nevertheless, right? Nevertheless, we recognize from this that T alpha beta is equal to T beta alpha, right? That the energy momentum tensor constructed in this way is in fact symmetric, right? That is certainly clear because of the appearance of the P alpha and the P beta. Right, so symmetric. Remember that tensors, can have a symmetry because, for example, the electromagnetic field strength tensor that was not symmetric was antisymmetric. F mu nu was equal to minus F nu mu. Here it is symmetric, right? So that's one aspect of it. And the second aspect is that now we worry whether this thing is actually manifestly Lorentz invariant. And so now we play the same game we do before. Right, and we write T alpha beta of x. We can rewrite it as an integral in d tau. We actually go back to this expression here, which is just as good, except it's not manifestly symmetric, but who cares? And we are going to play the same game we did before, that is, write this as a delta function, delta 4 of x minus x of tau. Right, and times P alpha and dx beta by d tau. So this is still true. Why is it true? Because the delta naught, the naught component of this delta function, can be written as a delta of t minus t naught, which gets rid of the integral over tau, right? And you pick up a Jacobian factor, which gives dx by d tau by dt, and that turns into the d by dt that we have here. So we conclude from this that, in fact, the energy momentum is a tensor. The momentum is a tensor because it is written. What is the rule that we're using in this case? The rule we're using that if you have two 4 vectors and you take the product, direct product, right? One index alpha, the other index beta. You take the direct product, you're still going to get a genuine, Lorentz, in this case, tensor, right? So that is okay because this is a 4 vector. Why is this a 4 vector? Well, because the derivative with respect to the proper time, which is an invariant, the proper time. So this is a 4 vector. This also behaves nicely, and so everything is done. So that concludes the proof, right? And so now the other thing we want to show is that d by dx alpha, T alpha beta of x is equal to 0. Right? And well, this is again an exercise. And how is this exercise going to be done? Well, it is going to be done the same way we did it for electromagnetism. That is, you look at the spatial components, the I components, and you take the derivative with respect to this delta function. So you get a gradient with respect to this x, which you can write as minus a gradient with respect to the trajectory, right? And then if you do that, you end up with the naught component of the energy momentum tensor, and so this is conserved. So that's another important result. And so we'll put a box around that, and we can put a box around this one too, because those are the two most important properties of this object, right? And so this was all for a single particle which has a given trajectory, right? And so And now we go back, all right, go back to charged particle, right, charged particle. And so now we have the T mu nu. What T mu nu? Well, we have this T mu nu here, right? Well, this T mu nu describes the energy momentum tensor that is associated with a particle that follows some trajectory. So that is related, of course, to the energy of that particle and the momentum of that particle at an instant of time, right? So here we have a charged particle that does the same thing, right? It moves along a trajectory x of t. But the new ingredient we want to add is that the reason why it follows a certain trajectory is because there is some sort of E or B field here, right, which acts on the particle in accordance to the Lorentz force equation, right? So that means that when we discuss the energy momentum tensor, T alpha beta of x, we have to introduce a new concept, right? Because if the particle is in an electromagnetic field, then we do have the energy momentum tensor that is associated with the particle, which has to do with its momentum energy. But we have another component, which is the energy momentum associated with the electromagnetic field, right? Very good. So that means that we should really talk about the total energy momentum tensor, and that will be the T alpha beta of x that refers to the particle, right? Or it could be more than one. Of course, if there's more than one, then it just adds up, right? That's the nice thing about energy, right? It always adds up. You just, if you have many components or many particles, you just do a sum, right? And, but nevertheless, if it is moving due to the effect of an electromagnetic field, then we should add the T alpha beta of x of electromagnetism, right? Which is the T alpha beta of the electromagnetic field. Now, does the electromagnetic field carry energy and momentum? Yes, because we learned that when we read Jackson, right? We know that there is an energy density which is proportional to E squared plus B squared, and there is a momentum density which is given by the good old, what's the guy's name? Energy momentum density given by the momentum density given by the Poynting vector, right? The Poynting vector is the E cross B part, right? So this one, see above, right, means that blackboard there. And so this one will contain the E and B fields in some way. So T alpha beta of electromagnetism of x, well, it is supposed to be a tensor, right? So it is F alpha beta. Well, no, certainly not, for a number of reasons, right? First of all, because this, of course, is the field strength tensor, right? F mu nu or F alpha beta for electromagnetism. This is not going to work in this way, right? The first reason is that this thing is, yes, that's the second reason, that the symmetry is wrong, right? This is antisymmetric and this one is symmetric, so that's not going to work. The other thing that we do know, and somebody just mentioned that, is that the energy density or the momentum density, and therefore the T alpha beta, has to be quadratic in the fields. It has to be quadratic. There has to be an E squared or B squared coming out of this at some point. So that means there's going to be two Fs, okay? There's going to be two Fs. Now, when you have two Fs, you have to construct now an object where only two indices are left over, which means you have to have a contraction, right? You have to have a contraction. So, for example, you can have F alpha gamma and F gamma beta in this way, and this would now work. This would now work. In fact, it is symmetric in alpha and beta because you have the two Fs that enter symmetrically, and you have, of course, to start with four indices, but the four indices can be reduced by just doing some sort of dot product, right? A contraction, right? Contraction is a dot product. Well, but it turns out that this is not the only thing that you can construct, because you can do dot products in some other way, right? You can construct, for example, you can take the F, right, and you can do gamma delta and then F gamma delta. So you can do some sort of a trace, and that will be non-zero, because if you interchange these indices, you can interchange those as well, and it's non-zero. So this is also a candidate, right, where you just trace over all the indices. But of course, the index structure now is not what you want, because you summed over all those indices, and so all the indices are gone, right? So how do you make this into a two-index object, which is manifestly symmetric under the interchange, is that you add an eta alpha beta, right, which you remember is a tensor and has all the right properties. You can do that as well, right? And so you can have both, right? And so now what you do is you write this as C1 times that plus C2 times this, right? Because you don't know what a mixture of the two things. There's nothing else, by the way, that you can have, right? And so you find that by a thing that I will just say in a second, that this has to be minus a quarter. This has to be minus a quarter, right? And how do you see that? Well, you will see that because if you take an arbitrary linear combination, then you do know then when you take the not components, remember before the not component was just the not component here was just the energy, right, part. So here we're going to have also the energy part. So what is the energy part of an electromagnetic field? Well, this is equal, it has to come out to be 1/2 E squared plus B squared, right? And so it has to come out this way, and that fixes the two coefficients. It fixes those C1 and C2. So this is 1, and this is minus a quarter, and that will give that. So, and of course, the other thing that we know is that T naught I of electromagnetism is equal to E cross B, ith component. This is the so-called pointing vector. Right? So we know that as well. So that uniquely fixes the relative signs, okay? But it is important to realize this kind of arguments, and the power that they have, because we're going to use those, and Einstein used those, in general relativity as well. And so let me repeat the argument one more time, is that if the T mu nu, or the T alpha beta, is a tensor, then there's only certain ways that you can construct it out of other things, right? For example, in this case, the F alpha beta, right? And so you only can have certain combinations, and the number of combinations is usually rather limited, right? Especially if you're saying that it has to be quadratic. There's only 2 terms, right? And then by some suitable limit, you can take the right limit. Yes?
What about FF twiddle?
Yeah, you could have an E dot B term as well, but that's not there. Yeah, so this is the correct combination. Yeah, you could use the epsilon symbol as well. Yeah.
And we said that the total has to be symmetric in the indices because of this?
It definitely has to be symmetric.
Okay.
It has to be symmetric. Yeah, well, this one is symmetric too, but it has to be symmetric because we had it for a particle, right? And so here it comes out symmetric as well. So if you were to try to something that is not symmetric, then you would find out that you don't get the correct limit, right? So there's only so many combinations that you can have, and there are not only 2 which are in fact linearly independent, which are these 2, right? You can try to construct something a little bit more complicated, but it would come down to the same thing. And so we are left with one last item, right? What is the one last item with this guy here? We might wonder whether we might wonder whether the energy momentum tensor for the electromagnetic field is actually conserved, and whether when you take the derivative of this, you get 0. And so that will be left as an exercise again, right? And so you take the derivative of this. So you're going to get derivatives. Remember that this is a density, right? So it always depends on x, right? It depends on x. Of course, the eta is not x dependent, right? And so you have to take a whole bunch of derivatives, right? And so what are you going to use to show eventually that this is 0? Well, the only thing you can use is some knowledge about what the derivative of f with respect to x is equal to, right? But that is, of course, precisely what you have from Maxwell's equations, right? From the equations we had before about the divergence of f being equal to minus j, for example, right? And then the second homogeneous equation as well. So there's a little bit of algebra that you have to do here, but you can in fact show that, again, this is the only object that is, this is the right combination, that this combination is also conserved. So now these kind of arguments are very important because we are going to repeat them again in the case of general relativity, where we're going to talk about other tensors which have to do with the curvature and their properties, and how you can restrict those by just invariance arguments. Anyhow, I think we're out of time, so this is it for today's lecture. The plan is that in the next lecture we're going to talk briefly about angular momentum, and that will take, only 10 or 15 minutes, and then we're going to talk about the perfect fluid, which will take about 15 minutes or so. And then perhaps in the next lecture we can already start talking about the general theory of relativity. So leave special relativity and move on to GR. That's the plan. All right, so I'll see you on Thursday.